8 of the course Irrigation Engineering. In today's lecture, we will study about diversion headworks. What we mean by diversion headworks, what are the different components, their functions. So what is a headwork? Any hydraulic structure which supplies water to the off-taking canal is called a headwork. Any hydraulic structure which supplies water to the off-taking canal is called a headwork. So the arrangement which is made when we want to divert water from the river to the off-taking canal, that is known as a headwork. Now headworks may be divided into two classes. We have storage headwork and we have diversion headwork. So what we mean by storage headwork, it comprises the construction of a dam across the river. It stores water during the period of excess supplies in the river and releases it when a demand overtakes available supplies. So headworks can be divided into storage headwork or diversion headwork. In storage headwork, basically we have a dam which stores the water, and the duration is relatively longer relative to the diversion headwork if we have storage. So a dam basically regulates the flow of water in the river. We store the water and then that water is released during the period of low water in the river. You see why we construct the dam. If we have enough water available in the river, that is sufficient to meet the demands in stream and outstream, then no need of construction of a dam. But as we already studied that, for example, in case of Pakistan, in the rivers, during summer time, we have more water because the source for this water, these are glaciers in the northern part of the country. So during the summer time, more water is available, so sufficient to meet the demands. But during winter time, when the temperatures are low, so the rate of melting of glacier slows down, contributing less water in the to the rivers as compared to the summer. So that's why we need to construct dams to store the water during peak flows, and when the water in the river decreases, not sufficient to meet the water demands, so we can supply the water from the dams. So these are storage headworks. We will study about the dams in detail later on in this course. The second one, that is diversion headwork. So what is this? It serves to divert the required supply of water into the canal from the river. So diversion headworks, it serves to divert the water from the river to the canal. Diversion headworks are constructed on perennial rivers. So rivers in which throughout the year water is flowing, perennial rivers. So these headworks, they are constructed on perennial rivers, and we divert the water to the off-taking canals. And we already studied about the canals, that the water is then supplied to meet the agricultural needs. Additionally, the water can be supplied for domestic purposes also. So we will study in detail about the diversion headworks in today's lecture. What is diversion headworks? As we already studied, that we divert the required quantity of water to the canal from the river through the diversion headwork. So we formally define it. The works which are constructed at the head of the canal in order to divert the river water towards the canal so as to ensure a regulated continuous supply of silt-free water with a certain minimum head into the canal are known as diversion headworks. So the works which are constructed at the head of the canal, start of the canal, at the head of the canal, in order to divert the river water towards the canal to ensure a regulated continuous supply, because the water that is supplied to the canal, that is regulated. So the head regulator that is operated to control the supply of water into the canal. We will study in detail about the canal head regulator. And silt-free water. So arrangements are made that the silt which is flowing in the river, that is removed from the water. For this we have certain measures in the form of silt excluders and silt ejectors, and the silt-free water with a certain minimum head that flows into the canal. So such works are known as diversion headworks. This is an example of a Mandara headwork which is constructed on the Swat River, and this is the headworks, that is Khanki headwork. Clear? Now these headworks, so the Khanki headworks, that is on the Chenab River. Clear? So these headworks basically divert the water. As you can see here, that the water will flow in the river in this direction. This is the upstream, and we have, this is the downstream of the river, and here the water is diverted. This is the canal head regulator, where controlled supply of water can flow into the canal, and this is actually the canal. A diversion headwork serves the following purposes. It raises the water level in the river so that the command area can be increased. So it raises the water level. The head is increased so that water can travel for longer distances due to gravity. It regulates the intake of water into the canal. So as you saw in the previous slide here, that we have these canal head regulators here. Similarly, this is canal head regulators. So through these canal head regulators, controlled supply of water flows into the canal. So it regulates the intake of water into the canal. It controls the silt entry into the canal. So you can see here, especially in this picture, that the water flows and it carries the sediments. Now, sediments, if they flow in the water in the canal, so these sediments can be deposited and they influence the discharge carrying capacity of the canals, and also we want to supply silt-free water to the agricultural lands. So in the diversion headworks, arrangements are made, measures are taken to remove the sediments or minimize the sediment inflow into the canals. We will study in detail what are those measures that are adopted to control the silt entry into the canal. It reduces fluctuations and stores water in case of short supplies. So the other purpose of diversion headwork is to reduce the fluctuations. As you can see here, that by construction of this weir or barrage here, which you can see, this is a barrage or weir, clear? So it raises the water level upstream. Now, as I already said, that the water level in the river can fluctuate. So this fluctuation will have impact on the water flow to the off-taking canal. So because of the diversion headworks that we construct this arrangement here, these fluctuations are reduced. So that is why this is one of the purposes, that it reduces fluctuations in the river and consequently fluctuations in the canal flows, and stores water in case of short supplies. Although diversion headworks as compared to storage headworks, you see the diversion headworks here, the storage, that is relatively very small as compared to the storage headworks. But still it is possible that we can store some quantity of water that can be supplied in case of short supplies. So these are a few examples of headworks that we have in Pakistan. We have Islam headworks, Balochi headworks, and Suleiman Ki headworks. Now in this picture you can see that we have this river water which is flowing here. We have this diversion headworks that you can see here, and the water is diverted to the off-taking canal. Similarly, in this example, you can see here, so the water is diverted into this off-taking canal. Remember, it can be more than one canal, depends on the requirements, but the works which are constructed on the river to divert the water to the off-taking canals, these works are known as diversion headworks. We can also have these storage headworks as we discuss, in which case we have this dam here that we can construct. So these are storage headworks, and from the dams we can also divert canals. Like for example, we discussed the Ghazi Barota power channel. So that is actually the canal which takes water from the Tarbela dam. Now we start with the weir. So a weir is a solid obstruction put across the river to raise its water level and divert the water into the canal. So we already studied about the basics of the weirs. in fluid mechanics and hydraulics. So a weir is a solid obstruction put across the river to raise its water level and divert the water into the canal. So the diversion headworks that we studied so far, you can see that we raise the water level by construction of a weir. So weir is nothing but it is a solid obstruction that is put across to the river to raise its water level and divert the water into the canal. If the major part or the entire ponding of water, because we create this ponding of water upstream side of the weir, if the major part or the entire ponding of the water is achieved by a raised crust, means crust of the weir, and a smaller part or nil part of it is achieved by the shutters, then this barrier is known as a weir. So in case of a weir, you can see here this is weir without shutters. Shutter means gates, small gates that are provided on the crust top of the weir. So this is a solid obstruction. We will study in detail. Can be made of concrete, can be made of masonry. So you can see here that weir without shutters, the total ponding by a raised crust. You can see here that this weir, it is put across the river and it raises the water level upstream. When we have weir with shutters, you can see here that a shutter is provided. So in this case, maximum ponding is done by the raised crust. You can see here P1 is the ponding that is done by the raised crust of the weir. So that is P1. Also ponding is done by the crust of the shutter, that is the water can be stored up to this level here. But in case of weirs, this P1, which is the ponding by raised crust of the weir, and P2, that is the ponding by the shutter. So you can see here that in case of weir, this P1 is much greater than P2. We will call this type of structure as weir. So weir can be without shutters, it can be with shutters. So it means that in case of weir, maximum ponding is done by the raised crust of the weir, and a smaller part or nil part of ponding is achieved by the shutters. If a weir also stores water for tiding over small periods of short supplies with less volume, it is called a storage weir. This is not always the case. The weir that we have studied so far, that it is used for measurement of the discharge, the same purpose is served, and it raises the water level upstream because it is an obstruction that is put across the river. So it raises the water level and the water can be diverted, for example, in the canal. But if a weir also stores water, but that will be a small quantity compared to the dam. For tiding over small periods of short supplies, that will be with less volume, then it is known as storage weir. The main difference between a storage weir and a dam is only in height and the duration for which the supply is stored. So a dam, the height will be more as compared to the weir, because the weirs, they are commonly provided from 5 to 15 feet. The dam height is more. We will study dams in detail. A dam stores the supply for comparatively longer duration. Next we have barrage. If most of the ponding is done by gates and a smaller or nil part of it is done by the raised crust, then the barrier is known as a barrage, or it is also called a river regulator. You can see here that in case of barrage with a small raised crust, you see here that ponding by the crust, that is P1, and ponding by gate, that is P2. So in case of barrage, we have P1 is very small as compared to P2. It means that in case of barrage, most of the ponding is done by gates and a small or nil part of it is done by the raised crust. So you can see here that in barrages we have gates that are provided and maximum ponding that is achieved through these gates. So in case of barrage, if it is provided with a raised crust level here, raised crust, small ponding is done, but major portion of the ponding that is achieved through the gates. This is the difference between the weir and the barrage. In this case, you can see here barrage without any raised crust. So total ponding that is achieved by the gate. So P1, which is the ponding by the crust, now is 0, and P2, which is the ponding by the gate, that is actually the total ponding. So this is the difference between the barrage and the weir. So in case of barrage, the maximum ponding that is achieved by the gates, whereas in case of weir, the maximum ponding that is achieved by the raised crust, and a little or nil part of it is achieved by the shutters. For example, you see in this case there are no shutters, so the total ponding that is by the raised crust. This is the basic difference between a weir and a barrage. So a barrage is a diversion structure across a river fitted with a series of gates over its entire length for creating the required ponding. So now for diversion headworks, you can see that for raising the water level and diverting the water into the off-taking canal, we can either provide a weir or a barrage. So now we can understand the difference between the two. Now this is a cross section which is taken for a barrage. So you can see here that in this case we do not have any raised crust, which is shown here. It is like this one here, without any raised crust here. So this is the upstream side. This is how the water flows, and this is the downstream side. We will discuss the different components of the barrage in detail later on, that are written here. You can see here that this is the ponding level that will be in the normal case, and when we have flood, so we will have the high flood level. The water can be raised up to this level, and if we have excess water, that can be released downstream by opening of these gates. So for this hydraulic structure, you can see that protection is provided upstream for the scouring and for the seepage of water that can endanger the hydraulic structure. Similarly, you can see that downstream protection that is provided in the form of inverted filter, that is to act against the piping, because the material can flow. There will be seepage below the foundation of the barrage in case of alluvial soils. We will study this in detail. And the apron that is provided downstream to provide protection against the scouring. So this is a photo for the Pottery barrage, again in Pakistan. You can see here that this barrage consists of a series of gates, and the water level is raised upstream, and the water is diverted to the canals. You can see here the gates can be opened, the gates can be raised, and the water can flow through the gates downstream. So we will study the different components of the barrage later on in detail. Clear? What are written here, the sheet piles, for which purpose these are provided, the protection upstream and downstream. As you can see here, the inverted filter that is provided to relieve the uplift pressure. Clear? The piping which can take place because of the seepage, and the apron that is provided to protect against the scouring. Now, if most of the ponding or the entire ponding is done by a permanent raised crust is aware, then the efflux caused during high floods is quite high. What is efflux? It is the rise in the high flood level near the weir or barrage site. As we already studied before, when we have this as the structure, let's say we have any weir, so there will be a raise in the water level here. If you remember from hydraulics, the backwater curve. So this is efflux. Clear? This rising of the water level, this is known as efflux. In irrigation engineering, we call this as efflux. So the efflux caused during high floods is quite high. Why? Because the reason is that the entire ponding, or most part of it, that is done by the raised crust. Clear? So the efflux caused during high floods is quite high. On the other hand, if most of the ponding is done by gates, that is in a barrage, then gates can be opened during high floods, and the efflux, that is rise in the high flood level near the side, will be nil or minimum. So you can see this is the advantage of a barrage over the weir. That in case of barrage, maximum ponding is done by gates, so the gates can be opened during high floods, and the efflux will be nil or minimum. So a barrage type construction can be easily supplemented with a roadway across the river at a small additional cost. You can see here in this picture that a barrage type construction can be easily supplemented with a roadway. So this is a roadway. It can be done easily in case of a barrage as compared to the weir, because if I go back, you can see here that in case of a weir, then it is costly compared to a barrage. For example, you want to construct a road here, it will be more costly. But in case of barrage, it can be done with small additional cost. So this is the reason that barrages are almost invariably constructed these days on all important rivers. So now the weir, it has become kind of obsolete. Nowadays, barrages are almost invariably constructed on rivers. So we briefly discuss about the efflux to get some basic idea that I already explained here. So efflux is the rise in the high flood level of the river upstream of the weir or the barrage in case of non-erodible soils, or the bridge in case of non-erodible soils, or barrage as a result of its construction. So the idea here is that whenever we obstruct the flow, either in the case of a weir or a barrage or the bridge, because commonly we constructed bridges that cross the rivers, so this efflux phenomena, it will occur. You can see here efflux formation where or barrage or dam, or even in the case of bridge also, because we constrict the flow, this will result in rise of water level upstream. So rise in water near the site due to constriction. So this rise in water level, this is known as efflux. This is similar to that backwater curve that you studied in your hydraulic course. So this rise in water level is maximum just near the site of construction and reduces as we go away from it upstream. The efflux extends for a long distance on the upstream side. And this increase in the water level, it can continue for long distance upstream. And in some cases, it may be up to 20 to 30 kilometers. Clear? I show the picture in the hydraulics class. If you remember from there, if I teach you hydraulics. So this is efflux. You can see here that in case of a bridge, because of the construction, the bridge piers, so you can see that it will give rise to this phenomena known as efflux. And there are research studies conducted to calculate this efflux. That construction of this bridge, how much will be the efflux? Similarly, you can see here that efflux, this is just the rise in the water surface upstream. So you see here that this line here, dark blue, it represents the water surface profile without a bridge. But now the bridge is constructed, so water surface profile with a bridge. So you can see here this light blue. So this is the concept of efflux. So because of the wear and the barrages, we obstruct the flow, the water level will rise. So that rise in the high flood level of the river upstream of the wear barrage, that is known as efflux. Now, before I go to this efflux, there are two other terms which are associated. Clear? So these are known as retrogression and accretion. Clear? So let me explain these two terms later on. First, we study about the comparison between the wear and the barrage. Or let me explain it here. You see that when we construct a wear, let's say this is a wear structure that is constructed on the river, or we have barrages. So what will happen, that it will store the water and the water level will rise, and excess water, it will flow over the surface of the wear, because the ponding can be done up to this level here. So above, the water will flow over the surface of the wear or through the gates in case of barrage. Now what happens is that the construction of a wear or a barrage across a river channel, it disturbs the regime of the river. How? The slope of the river upstream of the wear or the barrage, it flattens. Because of this ponding, what will happen, that the sediments which are carried by the water, these sediments will be deposited here. The sediments which are carried by the water of the river, these sediments, they will deposit here. Clear? So the slope of the river upstream of the wear or barrage flattens due to ponding up of water, and this results in deposition of silt in the pond. So this silt will be here, it will be accumulated here. You see, when the water velocity reduces, so these silt particles will get a chance to settle down. And what will happen is that silt free water, it will flow. So the silt here, let me write down here. We have the silt now here, that is deposited. And what we expect here is that the silt free water flowing over the weir. So this is silt free or minimum silt, clear? So we can say that silt free water. Now when this water, it flows over the weir, what will happen is that this silt free water flowing over the weir, or also in case of barrage, it will pick up the silt from the bed on the downstream river channel. So on the downstream, it will try to cause covering. So it will pick the water from there, clear? It will pick the sediments from the downstream because it is silt free. So what will happen is that it will pick the sediments from the river bed downstream, and this will result in progressing lowering of the river bed level. So what will happen is that with the passage of time, what will happen is that this bed level, it will lower. This will be lower. So this phenomena is called retrogression. This phenomena, this is known as, this phenomena is known as retrogression. So what will happen that the silt free water flowing over the weir, it will try to pick the sediments from the bed of the river downstream, clear? This is the downstream side. So what will happen is that it will lower the bed of the river downstream. This phenomena is called retrogression. So in alluvial soils, this is what from the previous studies, that in alluvial soils, this retrogression has been observed 4 to 7 feet. 4 to 7 feet downstream bed of the weir or the barrage in alluvial soils. So this is retrogression. The ponding is done behind the weir or barrage, so the silt will settle down, and as the water flows downstream, it will be relatively silt-free water. So this silt-free water will pick up the sediments from the bed of the river downstream, and this will lower the bed level downstream. So this phenomena, this is known as retrogression. Clear? And in alluvial soils, retrogression of 4 to 7 feet has been observed. Clear? So this phenomena will continue for a few years. Clear? Now, when silting is done here, when behind the weir or barrage, this area gets silted. Clear? So when the upstream pond is silted up and no more silt can be deposited here, that is the upstream, so water will flow under the gates of the barrage or over the weir, will then carry the total sediment load, because no more silt can settle here. It will now carry the silt, the water through the gates of the barrage or over the weir will carry the silt. Clear? So this silt will be deposited on the downstream side. And again, what will happen, that this will again rise. The bed level, it will again rise. So recovery of downstream bed levels up to its original level, and thereafter silting up or raising the bed above its original level. For example, after that it can become like this also. This phenomena is known as accretion. This phenomena is known as accretion. Accretion. So in short, the construction of weir or barrage will first result in retrogression of the downstream river bed and thereafter accretion. Clear? So you can see that this accretion, it is the reverse of retrogression. So the accretion or the process of recovery of downstream bed level is a slow process, and it may take 20 to 30 years. Clear? 20 to 30 years. So these were a few terms that were related, and you should have some idea about this. Now we discuss comparison between weir and barrage. So you can see here, this is an example of a weir, and this is an example of a barrage, a gated structure. So the maximum ponding that is achieved through the gates. But in case of weir, the maximum ponding that is achieved by the raised crust. So we discuss a few points to compare. So in case of weir, we have high set crust, and in case of barrage, we have low set crust. Ponding is done against the raised crust or partly against the raised crust and partly by shutters. Ponding is done by means of gates. In case of weir, shutters in part length but gated over entire length. You can see here the barrage, it will be throughout gated structure. But in case of weir, the gates can be part. You will see later on, we will discuss this in detail. Shutters are of small height. Gates are of greater height. Shutters are dropped to pass flood. Gates are raised to pass flood. No perfect control on river flow in case of wear. In case of barrage, we have perfect control on river flow. So these are the reasons why barrages are nowadays used instead of weirs. Operation of shutters is slow, involve labor and time. Gates are convenient to operate. Raised crust causes silting upstream. This is one of the disadvantages of the weir. But in case of barrages, less silting upstream due to low set crust. So the gates can be opened and the sediments can be flushed. But in case of the weir, it's very difficult to do the desilting. So in case of weir, no means for silt disposal. And in case of barrage, silt removal is done through the undersluices, which are gated structures. We will study in detail undersluices that are open, and the bottom water, it flushes the sediments along to the downstream side. Where shorter construction period, barrage longer construction period. The only advantage of the weir compared to barrage that is significant is that relatively cheaper structure and barrages are costlier. But you can see that the advantages of barrages are more as compared to weir. So that's why nowadays barrages, these are preferred over the weirs. Next, we discuss components of diversion headworks. So a typical layout of canal headworks is shown here. This is a typical layout of diversion headworks. It has the different components that we will now study in detail, their functions. So it consists of weir portion. This is the weir portion here, you see, where, as we already studied, obstruction across the river. So this is the weir portion, clear? Then we have the undersluices. So the undersluices here, these are the undersluices. We will study in detail their functions, etc. So this is the weir. The weir can be divided into bays with pairs, as you saw in the previous slides. You can see here, if I go back, you can see with the pairs, the weir is divided into bays. So this is the normal weir portion or the weir proper, that is the main weir. Now the undersluices, that is also portion of the weir, but we will discuss what is the function of the undersluices. So we have the main weir, then we have the undersluices, then we have the divide wall. So this is the divide wall, this one here. You can see that it extends upstream and downstream. This is the divide wall. So you can see it divides the undersluice portion of the weir with the normal weir portion. Then we have the river training works. So these marginal bunds and guide banks, these are the river training works. Then we have the fish ladder. You can see here, this is the fish ladder here. So the fish can travel upstream to downstream and downstream to upstream. For this purpose, the fish ladder that is provided. Canal head regulator. So you see here, this is canal head regulator with gated openings. So we regulate the flow of water into the canal. And we have various ancillary works such as the shutters, gates, etc. And silt regulation works. We will study all these components in detail. Silt regulation works that regulate the silt so that silt-free water can be diverted into the canal. So we start with the weir. Now we discuss in detail the components of the diversion headworks. So as we already learned that the weir is a solid obstruction put across the river to raise its water level and divert the water into the canal. Length of the weir is divided into number of bays by means of divide pairs. You can see here length of the weir that is divided into number of bays by means of divide pairs. Weir is aligned at right angle to the direction of main river flow, main river current. The right angled alignment is better and is common when a river bed is silty or sandy. This ensures lesser length of the weir, better discharge capacity and lesser cost. When the weir is placed at right angle to the main river current, this is better. Sometimes oblique alignment is necessary when river bed consists of gravel or shingle, which could otherwise enter the head regulator of main canal and get deposited into head reach of main canal. Next, we discuss classification of weirs. So classification according to design of floor, we can have gravity weir and non-gravity weir. What we mean by gravity weir? A gravity weir is the one in which the uplift pressure due to seepage of water below the floor that is resisted entirely by the weight of the weir. You can see here that below the foundation of the weir, we have the uplift pressure that is due to seepage of water below the floor. And the uplift pressure that will be in this fashion. Just in an example to let you understand, you see the water level here is high. So here the pressure will be this much. And if we have water level here, so it can start from maximum upstream to minimum or zero downstream. Can be zero if we have water level here. So it will be some uplift pressure here. So this uplift pressure, it acts on the foundation of the structure. This we will study in detail. In the next lecture, we will study about the seepage theories. We will study about the failure of weirs and barrages. So we will study in detail there. So now this uplift pressure due to seepage of water below the floor, when this is resisted by the weight of the weir, that is its body and floor, that is known as gravity weir. Same will be the case for dams. Later on we will study about the dam, so we will say gravity dam. So this is what we mean by that. That a gravity weir is the one in which the uplift pressure due to seepage of water below the floor is resisted entirely by the weight of the weir. So that is known as gravity weir. Same concept applies to dams. We will study dams later on. And we have non-gravity weir. So this is an example. Clear? In the non-gravity weir, the floor thickness is kept relatively less and the uplift pressure is largely resisted by the bending action of the reinforced concrete floor. Addition to the weight. Clear? There will be weight, but in case of non-gravity weir, the floor thickness is kept relatively less and the uplift pressure is largely resisted by the bending action of the reinforced concrete floor. So this can be an example. You can see here that reinforced cement concrete is provided in the foundation, and then the advantage is that the thickness is relatively small as compared to the gravity weir. And the uplift pressure that will be largely resisted by the bending action of the reinforced concrete floor. So this is a practical example of non-gravity weir. So the second classification is according to material of construction. So according to material of construction, we can have masonry weirs with vertical drop, rock fill weirs with sloping aprons, and concrete weirs with sloping glacis. Just like you saw here, this is sloping glacis here. So this is classification according to material of construction. So let us briefly discuss these. Masonry weirs with vertical drop. So this is an example of masonry weir, suitable for hard clay and consolidated gravel foundations at the downstream end of impervious floor. This is impervious apron here. A graded inverted filter is provided. This is inverted filter here, clear? This is inverted filter to relieve the uplift pressure. As I already stated before, due to piping, this uplift pressure. So inverted filter that is provided for the this is, you see here, block protection here. This is inverted filter here. So this is provided to relieve the uplift pressure. More detail you can find from the books on irrigation engineering. Rock fill weirs with sloping aprons. So you can see here that this is rock fill weir. It is also called dry stone slope weir. Simplest type of construction and suitable for fine sandy foundations. Such a weir requires huge quantities of stones and suitable where stone is easily available. Third one is concrete weirs with sloping glacis. You can see here sloping glacis. gently sloping here, 1 in 5. This is glacis, 1 in 4 upstream and 1 in 5 downstream. Sloping glacis. Suitable for soft sandy foundations. Suitable where difference in wear crust and downstream river bed is limited to 3 meter. When water passes over such a wear, hydraulic jump is formed on the sloping glacis. So on the sloping glacis here, the hydraulic jump will form, and as we studied in detail in the hydraulics course, that hydraulic jumps, they are very useful in hydraulic structures. Why? The reason is that they dissipate the destructive energy of fast moving water. So you can see here that these aprons, these arrangements are provided here to provide protection against the covering. So that's why hydraulic jump, it will dissipate the destructive energy of the flowing water. And also we have parabolic wear. This is parabolic wear example here. It is similar to the spillway section of a dam. The body wall of such a wear is designed as a low dam. A cistern, this is cistern, is provided at the downstream side to dissipate the energy. So here the water flows, hydraulic jump will occur, and the hydraulic jump will dissipate the energy. Just like you see here, I show you in this practical picture here, actual. You can see the hydraulic jumps that occur here, dissipates the energy. And in here, you can see that the hydraulic jumps can occur and it dissipates. Otherwise, if we do not have protection here, and this actually also called as the stilling basins. If you have studied in hydraulics, I teach in hydraulics stilling basins that are provided downstreams of the dams. So where the hydraulic jump can occur and dissipates the destructive energy of the flowing water. Otherwise, it will cause a covering of the river bed downstream. So a cistern is provided at the downstream side to dissipate the energy of fast moving water. The upstream and downstream protection works are similar to that of a vertical drop or sloping glacis wear.